Exergy balance will be implemented over control volume in this lecture. In the previous lecture, we tried to provide qualitative notions behind Exergy destruction and Exergy balance. Okay, so we started with analysis of a Carnot heat engine, and we analyzed what part of energy is available for doing work. Okay, so that is the simplest case where you can start making sense of Exergy. We did this by presenting information available in a TS data, how you can see that only a part of the energy is available for part of the heat that is transferred from a high temperature reservoir is available for doing work. We also rationalize this theme by looking at a Carnot engine from a molecular perspective. Okay, so there is some molecules that are coming from a high temperature reservoir. What do we mean by that? I mean, that is the kinetic energy of these molecules is representative of this temperature, high temperature reservoir. The average kinetic energy reflects the temperature of the high temperature reservoir. It collides and gives rise to unidirectional movement of a piston, which is work. However, when it does so, after collision, it still retains certain amount of energy. Okay, average kinetic energy again is reflective of the low temperature reservoir. Okay, so this is never zero. Therefore, only part of the energy available, thermal energy available, is converted into work. Okay, so this is the first. These are the examples that you should first understand to make a better sense of Exergy. And Exergy is inherently connected with entropy. Okay, so Exergy destruction is connected with entropy generation. So entropy can understood in a fundamental manner by looking at the microscopic definition. We have done this in the past. And then we derived in the previous lecture certain extrema relationship with respect to Exergy. Okay, so using, again, this is Exergy is the other side of entropy. So when there is entropy generation, there is Exergy destruction. Okay, so using this notion of, let's say, the number of ways of distributing thermal energy, we can understand why there is an entropy generation when heat gets transferred from regions of high temperature to regions of low temperature. Corresponding to entropy generation, there is Exergy destruction. So Exergy is the work potential. Work potential diminishes as entropy is generated. All right. And then we looked at entropy balance for the simplest system. Okay, so after setting up the equations, we start looking into how to apply these equations into certain systems. So we looked at the closed system, right? So that's the simplest system, and there can be different ways of transferring entropy, Exergy. As Exergy is a state variable, you can associate Exergy with a particular mass, or heat transfer or work transfer, right? So for a closed system, this term is zero, but there can be heat and work transfer. And we presented the formula associated with Exergy transfer associated with heat transfer and Exergy transfer associated with work and mass too. In this lecture, we will look at Exergy balance over control volume. Compared to a closed system, which is amenable, most amenable for analysis, control volume system are what you see in a typical engineering system. Here, not only there can be work transfer, work interactions and heat interactions, but mass can also flow into the system and out of the system. Associated with unit mass, you can associate Exergy So the problem becomes very similar to the way we thought about entropy balances, because entropy and exergy are not conserved quantities. There is a generation term in the case of entropy, and there is a destruction term in the case of exergy. So that's what makes a balance equation possible. Such a generation term and a destruction term is not there in conserved quantities when you think about, let's say, mass or energy conservation equations. So once you appreciate this fact that exergy is not a conserved quantity, this term becomes more common, more acceptable. Why the need for this term becomes obvious. So you have exergy into the system by mass input, and there is exergy out of the system by mass output. There can be heat interaction and work interaction. Okay, so all these things will, in this case, I mean, corresponding to this particular term, there is heat interaction that is denoted by this term, and work is given out. So work is done by the system on the surrounding. Therefore, there's a negative sign here. And all these things contribute to changes in exergy as balanced over this control volume. So the formulas we have already presented. So this is the exergy associated with heat, exergy interactions associated with heat interactions. And these are the work interaction term. This negative sign is here, and there is the mass input and associated exergy, mass output and associated exergy, and work potential that is destroyed, and you do a balance around the control volume. We can also do this in terms of rate of exergy changes. So this is just the same set of formulas per unit time. Okay, so this is in fact more relevant for engineering system, because many times we're interested in power production and so on. So in most of the engineering systems, you operate in a steady flow manner. So you take the previous equation, except that this term is zero, because you're always operating in a steady state. All the rest of the terms are retained. For a simple case as shown here, if you have just a single stream, there is exergy interaction associated with heat interactions and work interaction, and then exergy input and output, and then there is this destruction term, right? So which gives rise to decrease in exergy. All right, so we can represent these kinds of exergy changes when it goes from state 1 to state 2 in terms of specific exergy quantities per unit mass. So that is what is illustrated here. And if you neglect these two terms, there is a further simplification. If you have just the exergy changes because of heat interaction, work interaction, exergy that is coming inside the system, exergy that goes outside the system, and then exergy that is destroyed. Okay, so here this is the exergy that is coming in and exergy that is getting out of the system, right? So a useful quantity to define second law efficiency is what is called reversible work. So when you have this general equation as presented in the previous slide, when you have this general equation, when do you have reversible work? When there is no exergy destruction, that is when the work potential is not destroyed, when this term is equal to zero, that condition represents reversible work. So all the terms remain except that this term is 0. So it is, see, most of the things which we do with Exergy are analogous to what we did with entropy. Okay, so where there, when we say entropy generation is 0, that makes it reversible. Likewise, here, Exergy destruction is 0, that makes us give obtain the magnitude for reversible work. So in this term, which derived in the previous slide, this term is 0, which will help us in getting an expression for reversible work. So the reversible work is equal to incoming and outgoing Exergy, and the because of heat interaction, heat transfer, there is Exergy transfer. So this gives us a bound for maximum work that can be obtained when the system is operating in a reversible manner. So that's going to help us define the efficiency. For an adiabatic system, single stream, so this term becomes 0. Therefore, the reversible work is just the incoming Exergy minus the outgoing Exergy, gives the expression for maximum power that can be obtained from the system. Again, this is going to be helping us in defining efficiency measures. For example, if you consider adiabatic turbine, just implementing the concepts developed in the previous few slides, we can define for an adiabatic turbine what is the second law efficiency. So this is the real work you generate, divided by maximum work that is obtainable from the system. Okay, so the maximum work that is obtainable from the system is when the process occurs in a reversible manner. So that is obtained here. So that's what we showed in the previous slide. And then you have a work for a flow system, difference in enthalpy, because it's an adiabatic turbine. So that can be rewritten using equating Exergy destruction with entropy generation. This term, this expression, we derived this expression from the previous lecture, in the previous lecture. Let us look at a turbine again, but this turbine is not operating adiabatically. So there is some heat transfer associated between the turbine, associated with the turbine and the environment. So this is not an adiabatic turbine. How do you do Exergy balance? So we need to define the efficiency of this turbine. We have to obtain two terms, right? So let us look at the two terms. One is the real work that is obtained from this turbine. So this is just the energy balance, because this turbine operates at steady state. This term is 0. You can equate the power input to power output. Power input is via this flowing stream, that is the mass flow rate, times enthalpy associated with the input. You have power output, this is the work that is obtained from this system. There is heat transfer at a particular rate that corresponds to this, and this is the enthalpy that is taken out of the system per unit time via this mass flow rate. And typically you neglect changes in kinetic energy and potential energy, because these terms are much smaller compared to all other terms. So the work output here is this term. Note here we are looking at shaft work from a turbine. So this is the appropriate expression for the power output from the turbine. All right. Okay, so what is the other bound? Other bound is when there is work generated when the turbine is operating under reversible condition. What makes the turbine operate under reversible condition? When there is no exergy destruction, the turbine is operating under reversible condition. So just this is the overall exergy balance equation. Because of the reversible nature of operation, this term becomes 0. Because of steady state, this term becomes 0. Therefore, you have the rate of input exergy. So that will be mass flow rate of the system times exergy associated with the inlet. Then there is the exergy output from the system. And then there is work that is power that is obtained from the system and so on. Okay, so because there is no, it's a reversible operation, this term also becomes 0. Okay, so from here you can write the, get an expression for reversible power that can be obtained from the system. Just we are implementing the Exergy formula for which was developed in the previous slides. Okay, so and then what is the metric for efficiency? Metric for efficiency is the difference between the maximum power you would have obtained if the turbine was operating reversibly minus the power that is obtained in a real turbine. Okay, so that's the efficiency metric. With that, you can define the second law efficiency using this formula. Okay, so the real power output from the turbine that is operating under realistic condition minus divided by an ideal turbine that is operating in a reversible manner. All right. So again, I request you to contrast this analysis with entropy balance, which you implemented for a turbine, right? So the many things are very similar. Okay, so when the way you implement entropy balance and exergy balance, there are lots of similarities. But for analysis of engineering systems, exergy analysis is much more useful than entropy analysis. Okay, so so exergy analysis is what is done in the modern thermal design of many of the power machinery and so on. So you have to have a better feel for how to think through the system using exergy. Okay. All right. Then this is for second law efficiency for a device that requires work. In the previous system, we had looked at a work generating device, that's the turbine. Here we are looking at a compressor wherein the work is input into the system. Again, we can define so typically if the compressor is operating reversibly, you require lesser work. However, for a realistic system, the work that is required is much more than what you have for a compressor that is operating in a reversible manner. Okay, so this is just we are rewriting the efficiency in terms of entropy generation. So here, let's look at a concrete example. Here you are having a compressor. What does the compressor do? It takes up ambient air. Okay, so this is just at ambient atmosphere and ambient temperature. So this is actually a dead state, right? So the exergy, the work potential of this system, there is input into the compressor is 0, but the compressor does work and pumps this air into this system, which was initially empty. Okay, then it slowly starts pumping in compressed air into this system. Initially empty, I mean, in the sense that initially there is okay, empty in terms of exergy potential. Okay, so initially there is air with zero exergy potential, but you're pumping in air via a compressor. So the pressure increases from 1 atmosphere to some higher atmosphere, and the temperature, however, remains the same. So again, how do we first think about this? To look at the second law of efficiency, we need to have an ideal case. The ideal case is obtained by reversible operation of a compressor. So in the reversible operation of a compressor, there is no exergy destruction. This term is zero. There's only change in exergy as you pump in gases, air in this case, via a compressor. So work done is this term, and this term is because this is zero because the exergy of this system, that is the inlet fluid, is just it's a dead state. Okay? It is in equilibrium with the external atmosphere. Therefore, this term is zero. This is the balance after you start pumping it. This is the initial exergy of the system. To begin with, it was a dead state, and then you put in a certain amount of mass into the system. That's the exergy that is accumulated because of the compressed air, which is filling up this particular enclosure. All right. So we have just implemented this expression into this in this expression, right? All right. Okay. So what is the other bound that was required? There is a realistic when the compressor doesn't operate in a reversible manner but operates in a realistic condition. So that is obtained. Okay. So before that, so here we're just calculating phi 2. So phi 2 is obtained in the following manner. So what does a compressor do? Compressor just increases the pressure. Okay, so if you look at the temperatures, the inlet fluid is at the atmospheric temperature. Even in this enclosure, the temperature is only 300 degree Kelvin. Therefore, this term would be zero because T2 is just the same as the external ambient temperature. This term is zero. But what is changing is the specific volume. As the compressor operates, the specific volume decreases, right? So there is, in a way, that is what is giving rise to increase in work potential. In fact, one way of storing energy is in compressed air. Okay, so that's one of the method of mechanical form of energy storage is just compressed air, right? All right. And typically for this system, you can neglect kinetic energy because there's no center of mass motion. And this is also negligible compared to other terms. So all you have are these two terms for phi 2. And then this is the overall mass that is accumulated inside the enclosure. So then how do we compute S2? This we obtain by using the TDS relationship that we saw in few probably in 4 or 5 lectures. Previously, we have seen this. We looked at 2 TDS relationship. Using that, we can obtain this, compute this expression, right? So, for example, here, so what we're trying to do is using the TDS relationship, we can, there's one TDS relationship involving change in pressures, other involving change in volume. So here we have used the TDS relationship involving changes in pressure. You can just refer to that, and then we have implemented this term. This term we have obtained by just using ideal gas, assuming that air is ideal gas. Therefore, you can get the specific volume at this pressure using this expression, a specific volume at the atmospheric pressure by assuming temperature to be that of the atmospheric temperature and the pressure to be that of atmospheric pressure. So this term, just from ideal gas, we simplify, and this term we simplify from the TDS relationship. So with both these terms, you can get phi 2, and from once phi 2 is available to you, you can get the maximum reversible work. That gives us a bound. Okay, so for getting the efficiency of the compressor. Then once you know this, then you know the actual work which you utilized for running the compressor. From that, you can get a second law efficiency. So all these examples are from your textbook. So I encourage you to go over these examples. Okay, so because when things are abstract, many of the, when you present the formula and analysis, things may appear to be clear. Unless you work out the problems, you are never sure whether you are able to understand it clearly. So there are a set of solved examples, and there will be more homework examples that are going to be provided to you. So please go over them carefully to make sure you understand the material that is being presented. So in these cases, even the previous case, the case of turbine and a compressor, we could define something called reversible work, right? But in many cases, even that might not be possible. Okay. For example, in a mixing chamber, what are we trying to do here? You have two streams, they are mixed together, and then you get a single stream of which is at in between temperature. Inherently, this process is irreversible. Okay, you cannot really define a reversible case for analyzing these kinds of processes. Okay, so mixing is inherently irreversible. Mixing, because there is always a temperature difference, and these two streams with different temperatures are brought together to get a single fluid stream at a particular temperature. Okay, so when you do this, how do you define the second law efficiency? Is the mass flow rate out of the outlet stream times the exergy per unit mass of the outlet stream divided by the inlet exergies. Okay, so that's the way so you look at systems where there is inherent irreversibility associated with the process. Okay, so you cannot really define something of a reversible system because there is no the mixing doesn't operate in a reversible manner. Okay, so and then we can get to exergy destruction, again entropy generation by using other balances which we have seen all in the previous lecture, and an entropy balance. So another case where there is inherent irreversibility is in a heat exchanger. Okay, so there is always a heat exchange from a hot stream to a cold stream. Okay, that's what a heat exchanger does. So again, there is no reversible case in this scenario. Okay, so you define second law efficiency in a slightly different manner when in scenarios where you cannot really come up with a reversible process to analyze your process. Okay, where you were able to do that in the previous two examples, a turbine and a compressor, but in this case, a reversible process cannot be visualized, okay, cannot be accomplished. So how do you define exergy efficiency of in a heat exchanger, second law efficiency of a heat exchanger? You have the exergy of a cold stream divided by the exergy of a hot stream. Okay, so this is the mass flow rate of the cold stream, this is the mass flow rate of the hot stream, And then these are the exergy gained by the cold stream. Psi 4 is the exergy here and per unit mass, and psi 3 is the exergy at this particular point. From here, we can again define entropy generation, exergy destruction. So that brings us to the end of presentation of second law of thermodynamics. In a way, we have presented all laws of thermodynamics, the first law, second law, and the third law in a very limited manner. From here, there are two approaches towards utilizing this law, these laws. So we will look at two broad applications. Okay, so one application is how do you use these laws of thermodynamics to obtain thermodynamic properties. Okay, so what can be measured easily, what cannot be measured easily. You will, whatever that can be measured easily, you will try to use quantities that can be measured easily and then get an idea of what cannot be measured. Okay, so, and then certain kinds of manipulation are required for doing this. So that's what we will first do. That's called thermodynamic property relationship. And then there is another class of applications involving power systems. Okay, so these are two broad applications which will be the focus of the rest of the course. Thank you.